Imagine trying to cool your computer with, say, a tiny diamond blanket, or finding out that the light source that makes your iPhone smarter involves uh, microscopic star explosions. That's not science fiction. That's just the reality of modern microchip science. And welcome to the Deep Dive, where we take your pile of sources and find the gold inside.
Today we're digging into a fantastic piece by Samuel K. Moore from IEEE Spectrum. It's called The Top 8 Semiconductor Stories of 2025.
And it covers, well, everything. We're talking heat management, global supply chains, government policy. Our mission here is to unpack all of it to give you a real shortcut to understanding the future of computing.
Right, and this isn't just a list of cool gadgets. It's really a look at the long and winding journey a technology takes from, a lab idea or even just raw material to an actual commercial reality.
That lab-to-fab gap you hear experts talk about.
Exactly. We're tracking those long and twisting trips that technology makes to close that gap.
Okay, so let's start with the big one, the fundamental physics problem. It always seems to start with fighting physics.
It does. And first up is heat. As chips get smaller, they generate an incredible amount of heat. It's like a tiny thermal runaway reactor.
You're fitting a city's worth of computing into a matchbox, basically. And if you can't get that heat out, everything just grinds to a halt.
It does. It's called thermal throttling. So the big breakthrough is the work of Stanford professor Sravanti Chowdhury and her team. They found a way to literally grow diamonds inside the integrated circuits.
Wait, grow them inside the chip?
Right inside, just nanometers away from the heat-generating transistors.
And we're talking about actual diamonds here, the material that's like one of the best thermal conductors we know of.
The very same.
Yeah.
And that was the whole challenge, figuring out how to integrate it. The result was pretty amazing. They created radio devices that were more than 50 degrees Celsius cooler.
50 degrees, wow.
Yeah. And that paves the way for much better thermal management, especially in these new 3D stacked chips where heat is just the biggest nightmare.
Okay, that's incredible. So from managing heat, let's talk about creating light. Specifically for extreme ultraviolet lithography, EUV. This is the method used to write the features onto the chips.
And the light source is the key. It's just this incredibly complex contraption.
And the article had some amazing language to describe it. It mentioned supernovas, atomic bomb blasts.
It did. And it's not really an exaggeration of the physics involved. What ASML, the company that builds these, figured out is how to take these tiny droplets of molten tin and just blast them with incredibly high-powered lasers.
And that creates the light.
It creates a tiny contained plasma, like a microscopic star, that emits the exact wavelength of EUV light they need. It's this controlled, superheated flash thousands of times a second. It's just epic engineering.
It's hard to even wrap your head around that, but all that complexity, that makes EUV systems astronomically expensive.
It does. Which brings us to the next story, a potential competitor called nanoimprint lithography, or NIL.
Right, this was reported by John Boyd in Japan, and it's a completely different approach.
Totally different. Unlike light-based EUV, NIL literally stamps the chip's features onto the silicon.
Like a molecular level printing press.
Exactly. And the huge milestone here was that Canon sold the first NIL system for actual chip making. This is a technology that's been in the works for decades.
So if it's that much simpler, why did it take so long?
Well, the concept is simple, but the execution is brutally difficult.
Yeah.
I mean, when you're stamping at a nanometer scale, any tiny defect, a single speck of dust, can ruin the entire chip.
And alignment must be a nightmare.
A total nightmare. But Canon clearly believes they've solved enough of those problems to make it commercially viable. It's a really exciting new path for fabrication.
Okay, let's pivot a bit. From the physics of heat and light to the physics of, well, just sheer size and density.
Right. And story 3 takes us to the absolute cutting edge here. 2D chips.
These are materials that are only a few atoms thick.
Exactly. And we've known about them for a while, but the big news came out of China. Researchers, Mingrui Ao, Xucheng Zhu, and their team, they managed to integrate nearly 6,000 devices made from molybdenum disulfide.
6,000 on a chip that's, what, 3 atoms thick?
3 atoms thick. And they used it to create a working RISC-V processor. So this wasn't just some simple test circuit. It was a real functional CPU.
That's a huge leap. But what about the quality? I mean, at that scale.
That's the most astonishing part.
Yeah.
Even using just lab-level manufacturing, they achieved a 99.7% yield of good transistors.
Almost perfect.
Which suggests that 2D materials are a very viable path forward, not just for some niche components, but for complex processors.
Which connects perfectly to the next big shift for the whole industry, right? moving from the current transistors, the FinFETs, to this next generation.
Nanosheets, or as they're also known, gate-all-around.
Can you break that down for us? What's the difference?
Sure. So if you picture the current FinFET transistor like a little fence, the new nanosheet architecture basically wraps the gate, the switch around all four sides of the channel the current flows through.
So you get much better control over the electricity.
Vastly superior control. Less leakage, better power efficiency is the next logical step.
Oh.
And Story 7 details this intense competition between TSMC and Intel to see who could do it best.
Right, and they were both reporting details of their SRAM memory for these new chips.
And this was fascinating. Both companies produced memory cells that were exactly the same size, down to the nanometer.
A dead heat.
A dead heat on density, but then there was a twist.
Ah, the synopsis part of the story.
Exactly. Synopsys, a design company, managed to design a memory cell using the old FinFET transistors that achieve the same density.
Which on paper sounds great. You get the same density, but with the older, maybe cheaper technology.
You'd think so. But the performance was significantly worse. It just couldn't keep up. And that really proves the point. Sheer density isn't the only thing that matters anymore.
I see. So you have to move to the new nanosheet architecture to get the performance and power benefits you actually need. You can't just cram the old stuff tighter.
Precisely. The design has to embrace the new physics of the structure.
This is a perfect transition, actually, from the density inside the chip to the problem of moving all that data outside the chip.
The data bottleneck. It's a massive issue. We've got these incredibly fast processors, but the connections between them are like a data freeway jammed at rush hour.
And the solution is to use light, optics, instead of copper wires.
For speed and for power. And this idea has been around for a long time, but it was always held back by cost and reliability.
So what was the breakthrough in 2025?
The breakthrough was integration. Broadcom and NVIDIA, working separately, both developed optical transceivers that were integrated right into the same package as the network switch chips.
So the component that turns electricity into light is now part of the main chip itself.
Exactly. And that's critical for slinging data between server racks in these massive AI data centers. It's fundamentally changing the blueprint for AI infrastructure.
And none of this works without a mind-boggling supply chain. Which brings us to story number 8.
Yeah, Samuel K. Moore mentioned this was his favorite. It traces the whole journey from silica, basically quartz sand, to this smartphone in your hand.
And what did that journey look like?
It was a 30,000-kilometer trip.
30,000.
I know. It starts in a quartz mine, goes through all these specialized chemical refining plants in different countries, then the creation of the silicon ingot, all the way to the finished product.
It really highlights how this is a global effort, totally dependent on flawless logistics.
Absolutely. The geopolitical component is just baked into that 30,000-kilometer path. Any friction anywhere along that line can disrupt the entire tech industry overnight.
And that reliance on stability and, frankly, on policy. That brings us to the last and maybe the most frustrating story.
Yeah, story 5. This one is about the U.S. TAPS and Science Act.
An act that promised billions of dollars to close that lab-to-fab gap we talked about at the start, to make sure great American research could actually be manufactured here.
Right. And the main vehicle for this was supposed to be the National Semiconductor Technology Center, the NSTC. It was a legally mandated $7.4 billion program.
So, what happened?
The Commerce Department just abruptly ended the public-private partnership that was set up to administer it. It was called NatCast.
And this was a surprise.
A huge shock.
Mm-hmm.
The reporting used the word vitriol to describe how it was done. It stunned a lot of experts who had spent years building this thing.
So why would shutting down NatCast such a big deal?
Because it was supposed to be the neutral, nonprofit intermediary. You see, scaling up new chip ideas requires these incredibly expensive pilot production lines. No single university or company wants to foot that bill alone.
So NatCast was meant to pool the resources.
Exactly. And when it was shut down, it also led to the closure of another group, the Smart USA Institute, which was working on digital twins for chip manufacturing. It basically stalled the entire U.S. effort to turn R&D into actual production.
So despite all the money promised, that gap between the lab and the fab is still wide open here in the U.S.
It is. It's a pretty sobering reminder that the journey can be stopped not just by the laws of physics, but by, politics.
Okay, that is a lot to take in. Let's try and wrap this up with the key takeaways from these stories.
I'd say the first one is that the future of performance is really a multi-front war. It's not just shrinking transistors anymore.
Right. It's also about solving fundamental physics problems, like getting heat out with diamond cooling or moving data with integrated optics.
Exactly. And second, manufacturing is getting really diverse. You have EUV competing with this completely different stamping method, NIL.
And then you have these wild cards, like 2D processors only 3 atoms thick. That could become mainstream way faster than we thought.
And the third, and maybe the biggest takeaway, is just how fragile this whole global effort is.
That 30,000-kilometer supply chain. And as the Netcast story showed, it all depends on stable policy. Science can break down barriers, but policy can build them right back up.
That's it. The next chip revolution isn't going to be one single discovery. It's this huge convergence of materials, techniques, and global logistics.
It's an incredible picture of simultaneous engineering across dozens of fields.
So it leaves you with a question. If the race to smaller, faster chips is really a race against fundamental laws of physics like heat and light, what's the next scientific field that's going to become a vital partner? Is it acoustics for vibration? Is it deep-sea material science? Something to mull over.
That is a fascinating question to consider. Thank you for joining us for this deep dive. If you found these insights valuable, make sure to subscribe so you never miss another one. We'll see you next time.